Okay, we're going to do some ratio test examples and get some more of those under our belt. This is what we had earlier today in our lecture. So let's take a look at something like this. Okay. So this here is going to be an. So we need that next term, an plus 1, and all we do is replace. Maybe we should just write it down again. Write this down as an. Negative 1 to the n over n squared plus 4. And the an plus 1 term is negative 1 to the n plus 1, n plus 1 over n plus 1 squared over 4. So you have this ratio. An plus 1 over an. This is why they call it the ratio test, right? An plus 1 over that an. Now remember what we discussed in lecture was don't write it as a complex fraction. Here's what we're going to write it as. You're going to multiply by the reciprocal. And the reciprocal of that an term. So this is n squared plus 4 over negative 1 to the n times n. So we're going to get to use algebra now. Negative 1 to the n times negative 1, n plus 1, n squared plus 4, and this is over n plus 1 squared plus 4. I'm going to put a bracket. Negative 1 to the n. All right. I think something's not right. I can see it right here. I can feel it. Plus 1 times that negative 1. So remember what we're going to do. We're going to do some algebra here. All right. Let's see what we have. Let's try some algebra. Okay. Let's focus on this portion here. So this portion is going to be negative 1 to the n times negative 1, n plus 1, n squared plus 4. And then you have n plus 1 squared plus 4, negative 1 to the n times n, and we're going to get this line to be straightened. Sorry. So you can see what cancels. And, we only get that term canceling, so it's kind of interesting, I guess. Use your absolute value properties. Absolute value of a product. Product of absolute values. Absolute value of a quotient. Quotient of absolute values. So we get n plus 1 squared plus 4. Absolute value of n. Now, at this point, the absolute value of negative 1 is 1. And then all these terms are positive, right? Because we're talking natural numbers. So here's what we end up with. N plus 1, n squared plus 4, and then we have n plus 1 squared plus 4 times that n. Now we're going to do a little bit more algebra here because we're going to have to take the limit here of this, and here's the algebra. We're going to multiply on top here. We're gonna foil this. We're gonna foil this. Okay, so we're gonna do some algebra here. We're gonna multiply. Got to multiply. And here's what we end up getting here. Looks like it'll be n cubed plus 4n plus n squared plus 4. Here's our numerator. And then down here we'll get n squared plus 2n plus 1. Don't forget to add that 4 times n. We're going to simplify some things here, right? N cubed plus n squared plus 4n plus 4. That's my numerator. And then in the bottom here, we get the n squared plus 2n plus 5. Don't forget to multiply that by n. So we have n cubed plus n squared plus 4n plus 4. And I'm going to distribute with this n. So I get n cubed plus 2n squared plus 5n. Now, this again is the absolute value of an plus 1 over that an. So we're going to take the limit of that. We're going to take the limit here as n gets big of the absolute value of that ratio, which is the limit as n gets big, n cubed plus n squared plus 4n plus 4 over n cubed plus 2n squared plus 5n. This is a calculus 1 question. We're going to divide every term by n cubed. N cubed, n cubed, n cubed. Divide every term by n cubed. And here's what we end up getting. Limit n goes to infinity, 1 plus 1 over n, 4 over n squared, 4 over n cubed. 1, and that eraser comes out always. It messes me up. 1 over 2 over n plus 5 over that n squared. So as you guys can see, we're going to take the limit here. So all of these go to 0, right, by properties of limits. And you end up with, ladies and gentlemen, we end up with the situation that this is going to be 1 over 1, and that's equal to 1. That's our limit value. Now, let's notice something here by the ratio test that we talked about this morning, that if the value of this limit is equal to 1, that's the out value, and it equals 1, then this ratio test that we just did is inconclusive. So we have an inconclusive ratio test. Okay, so it's inconclusive. So then you might say to me, okay, well, the ratio test is inconclusive. Well, we have to see one of those cases. You know, this is an example of what we did today. What do you do when it's inconclusive? When it's inconclusive, you have to try another test. And so this particular question, what we're going to try is another test, and we go back and we say, well, what can we do? Well, let's look at it. Oh, well, we have, if we notice something here, we have an alternating mechanism. So we're going to try looking at the alternating series test. So I say, okay, here's my Bn. We're going to look at n over n squared plus 4. And of course, this is a decreasing sequence. These terms are decreasing. It's simply because the denominator, which is n squared plus 4, is a lot bigger than my numerator. And so as n gets big, that ratio gets smaller. And so if we look at the limit now of that, we say, okay, that's the limit of, remember, divide by the highest power of the variable in the denominator, which is n squared. So that's n over n squared over n squared, plus 4 over n squared. And we're running out of space, so I'm going to get rid of this portion here. We don't need it. And my limit now will be 1 over n over 1 plus 4 over n squared. And so this limit's going to be 0 over 1 plus 0, which is going to equal 0. So sure enough, we know this series converges. And of course, this converges by the alternating series test. So that's kind of the idea here, right? We justify how this converges. Converges by AST. So that's kind of an example, or it's not kind of, it is an example where it's inconclusive. And, you know, this is kind of what you see by this test. All right. Let's look at another. Another example of this ratio test. 1 to infinity, n to the 10th power over negative 10 to the n plus 1. And, you know, in case you guys didn't know, that negative 10 looks like it's going to make this an alternating series test, but we're going to see what happens by this ratio test. Okay. This is an. In other words, an is n to the 10th over negative 10 to the n plus 1. And, all right. an plus 1, replace n with n plus 1. Right, here's how that works. Wherever there's an n, you replace it with n plus 1. So now that makes that n plus 1. That makes this n plus 1. But we can simplify just a little bit here. This is the 10th power, negative 10 to the n plus 2, because n plus 1 is 2, right? N plus 2, really. So let's look at the ratio. an plus 1 over an in absolute value. So the first term will be n plus 1 to the 10th over negative 10 to the n plus 2 here. Now this is times the reciprocal here. Negative 10 to the n plus 1 over n to the 10 in absolute value. So this is where some algebra comes in. Really properties of exponents. N plus 1 to the 10 times negative 10 to the n, negative 10. We're dealing with this property here. Now we're going to deal with this next one. And that's negative 10 to the n, negative 10 squared. And then I have an n to the 10th power here. And there we go. So what you can see here is this portion is gone. And actually, one of these is gone. So that's the power 1 now. So what's left here, absolute value, n plus 1 to the 10th power over negative 10 n to the 10th power in absolute value. So use your properties there of exponents, the absolute value n plus 1 to the 10th power here over absolute value of 10, absolute value n to the 10. The absolute value of negative 10 is 10. And this portion up here will be n plus 1 to the 10th power because n is positive. So we'll have n plus 1 to the 10th power over 10 n to the 10th power. This is absolute value an plus 1 over an. We're going to take the limit now of this ratio, which is going to be the limit of n plus 1 to the 10th power over 10 n to the 10th power. I can factor out my constant. And using properties of exponents again, because they're both power 10s, could write this as a quotient with a power 10. One over 10, hold on. Let's look at this limit. 1 plus 1 over n to the 10th power as n gets big. Now, this limit here, the inside here goes to 1 as n gets big. And so that goes to 1 to the 10th power, which gives you actually, 1. But the final answer is 1/10, and that certainly is smaller than 1. That's the limit value. It's smaller than 1. And that's what we need. We need this for convergence, or in fact, we should say for absolute convergence. So you guys can see that here. So this portion here goes to really 1 to the 10th power, right? Which is 1. So 1/10 times 1 is 1/10. This is what we're looking at. And we have absolute convergence here. So we have absolute convergence, which implies convergence. And again, this is by the ratio test. Okay. So let's continue with some of these. N factorial over n to the n. This is another factorial. So we had the request for factorials. Here's some. Here's another factorial question. And of course, we need the future term, an plus 1. Replace n with n plus 1. And this is what we get. All right, let's try this out here. We're going to look at here. The absolute value, an plus 1 over an. Absolute value, n plus 1 factorial over n plus 1 to the n plus 1 times the reciprocal. Okay? So let's do the algebra. Now, remember, we're going to do some algebra here with the exponents, and we're going to actually write this n plus 1 factorial here like we've seen earlier today. We're going to write it as, remember, by definition, you start with n plus 1, and then times n factorial really is what you guys see up in here. This is equivalent here. N plus 1 factorial is the same as n plus 1 times n factorial. And you say, well, why do I do that? Because I have an n factorial down here. And this is n to the n. We can't simplify that. We can simplify this as n plus 1 to the n times a factor of n plus 1, algebraically speaking, right in here. And we're left with that n factorial. So we worked with this portion here. Don't forget that's a plus, right? And we rewrote this as using properties of exponents anyway. Let's get that there. Okay, let's see what happens with our cancellation now. If we see this cancellation, we're going to get n factorial gone. We're going to get n plus 1 gone. And notice we're left with n to the n over n plus 1 to the n. Let's get our computer back here. So here's what we have. Absolute value, n to the n over n plus 1 to the n again. And these terms are all positive. And by properties of exponents, n over, that's n plus 1 to the n. Okay. All right. Now, we're going to take the limit of the absolute value of that ratio, which is the limit of n over n plus 1 to the nth power. So we have to figure out what that limit is. Working with what's inside, right? So dividing by the variable with the highest power in the denominator, that's an n over n over n. We get this limit here. N goes to infinity, 1 over 1 plus 1 over n to the n. And looking at this in terms of limits, we get this portion down here goes to 0, right? So we'll get 1 over 1 plus 0. It's 1 to the infinity power. Okay. So again, you might go out to calculus and you say, well, I need to know what this limit actually is going to be. Let's go out to calculus. And you say, okay, for calculus, we have the limit here as x goes to infinity, x over x plus 1 to the x power. We know is an indeterminate power. So we're going to let y be, and let's change that color. We'll keep it purple for calculus. We're going to let y be x over x plus 1 to the x. And that now means that natural log y is natural log of x over x plus 1 to the x. Pull out my x here by the power rule, right? This comes out. And so I get x natural log of x over x plus 1. And okay, yeah, it looks like we're okay here. And so if I say to you, as x gets big, what's the limit now of the right-hand side here, right? We're taking the limit of everything on the right. And that's x natural log x over x plus 1. Right? So x is getting big. We're really focusing on that right-hand side. And you say, why not the left? Because the left is a constant y, or it's not a constant, it's a function. But it's with the y variable we're looking at as x gets big. We want to see, where does that natural log y go to? This is kind of where we're at. We want to see where this goes to. Okay, and let's draw a better circle around that. Or maybe draw a square, rectangle. All right, so we got infinity times. Let's go see what's going on inside here again. What do we get here for this natural log? We're going to do that same algebra. That this portion is inside natural log 1 over 1 plus 1 over x. So when I take x getting big, believe it or not, this portion goes to 0. Okay? So you have the indeterminate product of infinity times 0. Okay. Right? Because this is what I want to really show you here. Maybe the notation is bad, right? That as x gets big, we know x over x plus 1 goes to 1, and the natural log of x over x plus 1 goes to the natural log of 1, and this equals 0. And that's where that 0 comes from, right in here. So we already have this x giving us this infinity. This is where you get that infinity times 0 as your indeterminate product. So, okay, so you guys know we have to rewrite this. We have to, what I've been saying in the calculus course, we have to fix this situation, meaning we write this as a quotient. And remember, we're going to differentiate. So we're going to write it as a quotient that's easy to differentiate. So that limit in red, and we'll keep it in red, we're going to write this as x gets big, natural log x plus 1 over x divided by 1 over x. And as you take that limit, you're going to find that you get 0 over 0, an indeterminate quotient, right? So we're going to have to take the derivative. But when we take the derivative, I'm going to use some properties here. I'm going to make this derivative a little bit easier. I'm going to write this numerator by properties of logs as the natural log of x plus 1 minus the natural log of x. This is still 1 over x. So these limits are equivalent. What I want to do is use L'Hopital's rule. The limit x goes to infinity, 1 over x plus 1 minus 1 over x over negative 1 over x squared. Because I'm differentiating by L'Hopital's rule, the numerator separate from the denominator, if you guys remember that. Now, algebra, the algebra portion that comes in here, limit x goes to infinity, 1 over x plus 1 minus 1 over x. This whole thing is going to be multiplied by negative x squared. And we get this limit here. X goes to infinity. We're going to keep it this way. This is x minus x squared over x plus 1. All right, let's double check to see if our algebra is okay, because we multiplied these terms here. This term times this, and it's negative times a negative is a positive, and then you get the x, and you go, okay. And then that's a minus x squared over x plus 1. So at this point, ladies and gentlemen, you might say again, okay, what's this limit? Well, the first portion is infinity minus, and you're going to get another infinity. So this limit here is infinity, and this is also infinity. And you're saying, I'm not quite sure why that is. Well, you know, you could do a couple of things, but if I divide by x, I get x over, yeah. So if you divide by the variable with the highest power here, just so you guys know, this portion gives you x squared divided by x over x plus 1 over x, which is just really x over 1 plus 1 over x. So the numerator here gets big, and the denominator goes to 1, and big over 1, right, is big. So this is why we have that big, and the sign here is negative. So anyway, it's an indeterminate difference here. So you guys know if there's an indeterminate difference, how you approach this is really to use some algebra again. And we have to look at the algebra that we can have available for us. So the algebra here, it looks like we can do, is add. And I have x over subtract, really, sorry. We're going to subtract here. And by subtracting, we get x squared plus x minus x squared. Everything over x plus 1. And so this is x over x plus 1. So this becomes the limit here of, now let's be careful. Okay, let's be very careful here. So I simply subtracted, say x plus 1, x squared plus x minus the x squared. And yeah, x over x plus 1 here. We get infinity over infinity. Okay, we get to use L'Hopital's rule. Limit x goes to infinity of 1 over 1, and that's going to be a constant 1. So this is the statement: as x gets big, the natural log y goes to 1. Now, something's bothering me. I think the sign is off. Not quite sure. Let's make sure our signs are okay. Yeah, I mean, looks good. So if you guys go over this and you find an error in the sign, please let me know. X squared plus x minus x squared. And I get x over x plus 1, and that limits 1. So we say this goes to 1, and that's natural log y. And then you say, okay, what's this deal? As x gets big, natural log y goes to 1. And this implies that we have the following. E to the natural log y goes to e to the 1, or we say y goes to e. So if y goes to e, ladies and gentlemen, when I'm looking at this limit, so you guys know, this is equal to e, which is smaller than 1. Because e is approximately 2.718. And I apologize, that's not smaller than 1, that's bigger than 1. I'm just looking at something here. Something's bothering me about this particular question. Yeah, let's make sure we wrote everything down. Okay. X plus 1. I see what's bothering me. We got it wrong here. It's backwards. This is where the issue is right here. X plus 1. Yeah. This should be, let's be careful here. Right? We got natural log x. This is x over x plus 1. That's where it was. And yeah, that's going to change things because something was bothering you. There's an error. I'll show you what I'm talking about. This is x. And this will be x plus 1. Okay. So, yeah, there it is. There it is. Let's do this here so we can get it nice. And this becomes really 1 over x minus that 1 over x plus 1. And now we're doing the same algebra. Okay. So we get 1 over x minus 1 over that x plus 1, ladies and gentlemen. And we're going to multiply. This is going to change this portion here. So that's going to give us a positive, x squared over x plus 1 minus x. And here's the idea. You still get infinity minus infinity. Okay, you still get that infinity minus infinity for the same reasons we looked at earlier. And when you continue, there it is. You got to use algebra. That's the fix. So we're going to add or subtract, really. And there it is. You have that little dyslexia there for numerator denominator. That's going to be a very big issue. X squared. This is minus x squared minus x. Now, there it is. X plus 1. And we found the error because I knew the limit was wrong. Because I know the answer, ladies and gentlemen. Okay. It's minus x over x plus 1. And we can factor the negative 1 times the limit of x over x plus 1. You guys know that this limit is 1, so this answer is negative 1. And that's the difference. Yeah, it's not positive 1, it's negative 1. Yeah, I said, wait a minute, I'm losing my mind. So x goes to not positive 1, x goes to negative 1. That's negative 1. So this limit is not e, it's actually 1 over e. And that's what I knew as the answer. So 1 over e, if we go back over here somewhere, we wrote it down. Yeah, this is not e, it's 1 over e. And that's a very different conclusion. All right, good. Now the universe is well. This is about 1/3, which is smaller than 1. Okay. This is what we're looking for. Okay, so this here is actually the definition of 1 over e. And anyway, that's why I knew the answer ahead of time, and it didn't pan out because we wrote down the wrong ratio. All right, 1 over e, 1/3 less than 1. What that means is we have absolute convergence by the ratio test. And absolute invergence implies convergence. And all of this is by the ratio test. Convergence, ratio test. The key phrase is here, but the rest is the work. All right, some fun examples. Let's do a few more. Yeah, okay, that was kind of interesting. We're going to do a few more here. We're going to do some more factorials. You know, the favorite of some people, we like factorials, right? So we have 2n parentheses factorial over n factorial squared. Okay. This is our an term, right? Here's an. So we'll say an is 2n parentheses factorial over n factorial squared. And then an plus 1 will become, now be careful, replace an n with an n plus 1. So I'm going to use a bracket now, because 2n plus 1 in parentheses factorial over n plus 1 factorial squared. So that an plus 1 becomes use some algebra. Distribute. We get 2n plus 2 factorial over n plus 1 factorial to the second power. So this is how we start looking at the ratios. Okay? So absolute value, an plus 1 over an. Start off with the future term, right? 2n plus 2 factorial over n plus 1 factorial squared. Now, this is times the reciprocal of n factorial squared over 2n factorial. Okay. So double check that we did everything okay here, because we're going to look at some of these details. We're going to have to stretch our back a little bit. All right, so let's get ready to do some algebra here. Now, what to point out to you guys here? We're going to use really the definitions of 2n plus 2 factorial because that's bigger than that 2n factorial, right? So let me show you how you handle that. That's going to be 2n plus 2, 2n plus 1, and then finally 2n factorial up there. And right in here, I'm going to focus. What does n plus 1 factorial mean? Well, it's n plus 1 times n factorial. So I'm having all the information I need to start some cancellation. So we have 2n plus 2, 2n plus 1 times 2n factorial, n factorial squared. N plus 1, n factorial squared, 2n factorial. So we're going to do some cancellation here. 2n factorial, 2n factorial. And right in here, let's do a little algebra. That this is n plus 1 squared, n factorial squared, so that we also have cancellation here with this here. So everything that's left here, if we said, well, what's left? We left 2n plus 2 over 2n plus 1, and then we just have, it looks like an n plus 1 squared. Two n plus 2, 2n plus 1 over n plus 1 squared. Now, these terms, again, ladies and gentlemen, are positive. So you have 2n plus 2, 2n plus 1 over n plus 1 squared. All right, now you might say, okay, how do we handle something like this? There's a couple of ways we can do this. We can simply use the algebra if you wanted. Well, let's look at this phrase down here. We get n plus 1 times n plus 1, which gives us n squared plus 2n plus 1. So we're going to get 2n plus 2, 2n plus 1 over n squared plus 2n plus 1. And if you wanted, maybe we just do it this way. We're going to multiply the top 2. We're going to use FOIL here. Let's do it that way. I was going to do something a little bit different, but that's okay. 4n squared, first term, outer term, 2n, inner term, 4n, last term, 2. So we really have this rational function to take a limit. So you're going to divide by, again, the variable with the highest power in the denominator for every term. The calculus 1 approach. And we get to simplify. And as you simplify here, we're going to get 4 plus 6 over n plus 2 over n squared. Everything over 1 plus 2 over n plus 1 over n squared. Now, this is the absolute value of an plus 1 over an. We're going to take the limit here. So as you guys can see, the limit as n gets big of this whole thing. I guess I'll write it again. 4 plus 6 over n plus 2 over that n squared. 1 plus 2 over n plus 1 over n squared. Ladies and gentlemen, this limit is 4, and that's greater than 1. So the series diverges. Remember, we really care about this limit value. Bigger than 1 means the series diverges by the ratio test. So we can say exactly that. Right? Diverges by the ratio test. Diverges ratio test. There you go. Anyway, there's a nice factorial question for you. And let's do a few more here maybe. Give you some more interesting examples. We have the series here of 2 to the n squared power over n factorial. Here's an, where an becomes 2 to the n squared over n factorial. An plus 1, 2 to the n plus 1 squared over n plus 1 factorial. So as we look at the absolute value of that ratio, and weird, let's get it, okay. Start with that future term, 2 to the n plus 1 squared power over n plus 1 factorial times n factorial over 2 to the n squared power. Using algebra. Okay, so, well, using algebra, let's see, what do we use here? I guess we have to keep it this way. Okay, we're going to keep it as 2 to the n plus 1 squared n factorial over n plus 1 times n factorial. We're doing that same thing we do with these future factorials. And then you say, but you have over here 2 to the n squared. We do. And let's write a straighter line. And let's notice a couple of things here. Cancel, cancel. Absolute value, 2 n plus 1 squared over n plus 1, 2 to the n squared. Now, at this point, we could do a couple of things. We can say that, listen, all the terms are positive, and we say 2 to the n plus 1 squared over n plus 1, 2 to the n squared. But I'm gonna say something that by properties of exponents here, you have these bases with these powers here. So you get 1 over n plus 1 times 2. You get n plus 1 squared minus n squared for this power here. Okay, and then you might say, well, what happens here with this? Well, let's see, let's expand here. You know, n plus 1 squared, if we write this as 1 over n plus 1 times 2, well, that's n squared plus 2n plus 1 minus that n squared. And so we subtract the n squareds, and so you have a 1 over n plus 1 times 2 to the 2n plus 1 power. All right, you guys okay with something like this? And then I'm going to put it together here. 2 to the 2n plus 1 over n plus 1. So we have an plus 1 over an. Okay, let's see what this becomes. So, ladies and gentlemen, let's think about this, right? We have to take the limit. So that limit of the absolute value of an plus 1 over an, we're looking at the limit as n gets big to 2n plus 1 over n plus 1. Okay. So as n gets big, what happens over here? My numerator gets big and my denominator gets big. But I want to say to you, look at that numerator. It's getting big, and it's going to get big faster than the denominator. But more importantly, I mean, if we look at this, this is big over big, infinity over infinity. We have to step out into calculus. And we say, what's the limit as x gets big here of 2 to the 2x plus 1 over x plus 1 because that is an indeterminate quotient, and we get to use L'Hopital's rule, and that the limit as x gets big, we have to differentiate 2 to the 2x plus 1, and we differentiate x plus 1, which we know is going to be simply 1 here. Now, we're going to have to go back and really dig deep. Here's what I mean by dig deep. And I guess we're out of colors. I don't know what other colors to use here for it. I guess we could keep it this way. So I'm going to say, we're going to call it a note, though. You know, if you differentiate 2 to the x power, well, that's 2 to the x natural log 2. Okay? But if we differentiate 2 to the u, we get 2 to the u natural log 2 du dx. And then this is by chain rule, ladies and gentlemen. This is the chain rule version. So this is calculus 2. You guys know how to differentiate exponential functions. You know how to differentiate with chain rule. So if we go back up here, here's what we'll say. This answer is 2 to the 2x plus 1 natural log 2 times the derivative of 2x plus 1. And that's 2 by chain rule. So this is equal to the limit as x gets big. If we go back and try to simplify some things, you can say, 2, let's write it down this way. 2 natural log 2 to the 2x plus 1, that's over 1. And again, anything over 1 is itself, right? And then this portion here we know is just a constant, and you can even call it, if you wanted, the natural log 4. It doesn't matter because you could use the power rule, but it's a constant. So I'm going to say it's the natural log 4, ladies and gentlemen, times the limit here as x goes to infinity of 2, and that power is 2x plus 1. So this portion, we know simply gets big, right? As x gets big, we know 2x plus 1 gets big, which is 2 to the 2x plus 1 gets big. And we get a constant natural log 4 times that infinity, and that's going to be infinity, ladies and gentlemen. So this equals infinity. Okay? So that's a positive number, by the way, natural log 4. So, a positive number times that infinity is infinity. So here's what we're showing. We're showing that this limit, using calculus, and ultimately L'Hopital's rule, is infinity, and that's very much bigger than 1, our criteria. So it's another interesting example of what you guys can see here, and it goes deep into knowledge of L'Hopital's rule, and it goes deep into derivatives, and this is why you can say your final is going to be comprehensive because you studied these things and we worked on this. So all together now, this is a divergent criteria for our series by the ratio test. So this simply, we say, diverges by the ratio test. And that's where it's at. So here's a good example of what you can see. And of course, these have some nice factorials that people kind of like. And let's do one more maybe. Let me double check. See if we have time for one more. We have energy for one more. And you go, okay. Well, let's try one more. Okay. Here we go. As you guys can see, a lot of good work there. 1 to infinity. Negative 1 to the n. 2 to the n. N factorial. And then you have this product, 5 times 8 times 11. And that pattern goes up to 3n plus 2. Okay. So here's our series here. And, you look at this portion here, you say, okay, I know what a factorial is, the definition of such, but this is not factorial down here, but it's something similar. It's a pattern where you take 3n plus 2, and you that's really describing what you do here to get the next terms here. Just use different values of n here. This is the description. So like when n is 1, then that portion is 5. So you start with the first term. That denominator there is going to be 5, ladies and gentlemen. And that'll be a negative 1 times 2 times 1 factorial. And then plus the second term, 2 squared, 2 factorial over now 5 times, now n is 2, 6, that's 8. So you do this pattern, forever. So anyway, I just want to point that out. It's not factorial, but it's actually a formula that just simply tells you to keep multiplying by that pattern, 3n plus 2. Anyway, by the ratio test, this is an. So we have an becoming negative 1 to the n, 2 to the n, n factorial, 5 times 8 times 11, all the way up to that 3n plus 2. Okay. And then we're going to look at the future term, an plus 1. Negative 1, n plus 1, 2 to the n plus 1, and you got n plus 1 factorial. Everything over. Let's write this down. Let me get the computer back. Everything over 5 times 8 times 11 up to 3 times n plus 1 plus 2. Because remember, wherever there's an n, here, 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 and here, you replace it with an n plus 1. So this is why you got an n plus 1, an n plus 1, an n plus 1, and an n plus 1. Okay, you're going to do a little bit of simplification, though. That down here in red, that certainly is going to be 3n plus 3 plus 2, 3n plus 5. Because you use that distributive property. So here's what you get. an plus 1 becomes negative 1, n plus 1, 2 to the n plus 1, n plus 1 factorial, over 5 times 8 times 11, up to 3n plus 5, which is kind of like saying just the next term, by the way. And let me write that down. Here's what I mean. 3n plus 2, and then that next term, 3n plus 5. That's going to be an important detail. Because that's the next term, right? When you add n being n plus 1. So let's look at that ratio now. Absolute value an plus 1 over that an, and you write this whole thing down, negative n plus 1, 2 to the n plus 1, n plus 1 factorial, over 5 times 8 times 11 times that 3n plus 2 and a 3n plus 5. And then don't forget, multiply by the reciprocal. And that's going to be right up here. 5, 8, 11 up to 3n plus 2 over negative 1 to the n, 2 to the n, n factorial. Absolute value. Okay, we're getting down there. All right. I'm going to cancel. Oops. I'm going to cancel all of this. We're going to cancel here. Now, remember, there's a lot more cancellation. So I'm going to do this in 2 steps because I don't have enough space. Negative 1 to the n times negative 1. 2 to the n times 2 times n plus 1 factorial, because I'm going to use properties of exponents here. Okay. And this is over negative 1 to the n, 2 to the n, n factorial. So I get to do another round of cancellation here. And sure enough, take a look again. Negative 1 times 2, n plus 1, n factorial, over n factorial in absolute value. And I'm going to get another round of cancellation. So I get this absolute value of negative 1, absolute value of 2, and I get absolute value of n plus 1. And I think I'm missing something here. Yeah, I forgot down here. See this here? Just be careful. 3n plus 5 is down here as well. So let's make sure we bring that along. So this is over 3n plus 5 in absolute value. All right. We almost forgot that term. Okay. Absolute value of negative 1 is 1. Absolute value of 2 is 2. And this term is positive. This is an n plus 1. And then this term is simply 3n plus 5. So, ladies and gentlemen, you end up with 2n plus 1 over 3n plus 5. And that's the absolute value of an plus 1 over an. So we're going to take the limit of that. We need the limit as n gets big of, let's just do it this way. Let's say this is 2n plus 2 over 3n plus 5. And so you guys know this limit is 2/3. Right? That limit will be 2/3. And 2/3 is actually smaller than 1. It's smaller than 3/3. So you might say, what did I do? Well, I could use L'Hopital's rule. You know, if we dive into calculus, and because you got infinity over infinity, if you wanted to do that, right? This is indeterminate, and look at this in terms of the variable x. And you get 2/3 being smaller than 1, which means we get absolute convergence. So here's what we can conclude. Absolute convergence by the ratio test, and that implies convergence. And this is all by the ratio test. So we got convergence by the ratio test, ladies and gentlemen. And that's another round of examples. In this case, the examples are from the ratio test. So this is a good deal, good setup, and you guys get to see some nice factorials here. Okay, those things that you kind of love. So I'll upload this for you guys today, and you can take a look. Okay, so I'll see you tomorrow.